So we've previously talked about plasticity, the stress-strain curve, the Ramberg-Osgood equation, and Newton-Raphson iteration to determine stress given a certain value of strain. We're going to continue on talking about uniaxial plasticity with uniaxial cyclic loading of metals. Let's first talk about the basic unloading and reloading behavior of metals, where we don't yield them in compression, but then we will get into a little bit more detail about cyclic loading, the cyclic stress-strain curve, and the massing hypothesis, the Boschinger effect. Alright, so here's a typical metal stress-strain curve that we have, and again, our slope of our linear portion we know is the modulus of elasticity. We get into the curvy portion and we have some yielding, we have some plastic strains that have developed through here. But instead of taking it all the way to this point, if instead we decided we wanted to unload it at a certain level of stress after we've reached our plastic strain, so we would go from our origin point to maybe this position 1 right here. And if we were to unload it, we were to release the loads, reducing the stress down to zero load, zero stress. This curve would typically be linear, and it would follow the same modulus of elasticity as what we had for our initial portion of our stress-strain curve. So we are starting at 0, loading it to 1, unloading it to 2. And should we decide to reload it, well, what we would find then is that we would reload it and it would follow this curve back up. And it would not yield at the same level of stress that we had previously. Instead, it would yield at this point pretty much where it left off of the stress-strain curve. So these red arrows are indicating our reloading, and then it would continue this way. And then it would follow this stress-strain curve very closely. Now all these things are a little bit approximate, but there may be a slight deviation right around here, but pretty soon you're on the same path as what you were as if you had never unloaded it whatsoever. Okay, so let's write a couple of those items down. Load past yield. Unload to zero load or zero stress. The reload path follows our unload path to where it left off the stress-strain curve. Okay, so that would be back to point 1. And then it continues on as if that unloading event never happened. Now the stress-strain response continues on as if the unload path has never happened. The actual material may have changed internally a little bit, but we'll deal with that later. We'll talk about that a little bit later. So one way to say this is that the material has remembered where it left off the stress-strain curve. It has material memory. Alright, so let's take a look then at fully reversed cyclic loading, where we're yielding in both tension and compression. Alright, so we're going to draw this as if it was in stress control. So I'm applying some sort of sawtooth waveform here. I'm trying to show equal amplitudes in tension and compression, but we are above our yield strength of our material. So this plot is stress versus time. So we have that waveform. If we were to look at the stress strain plot, I'll draw this out to the side. We have our initial loading. Okay, so now we're at this position right here. We'll call that position 1. We talked about how when we unload, we initially follow the slope of the initial stress strain curve. But something kind of interesting happens. If this is the negative of our yield stress, we don't usually wait until we get there to have yielding. We may end up having yielding at a position that's before the negative value of the yield stress. So what I mean by this is if this is, let's pick a number, 200 megapascals, I may have yielding and compression before I get to minus 200 megapascals. So I start the curve. Let me see if I can draw that a little bit better. I start to have this curvy part, and now I'm down here at position 2. And then I'll go from this position back up here. And again, I may end up yielding at a value that is now less than this initial sigma yield. So that dot corresponds to that dot right there. And then I continue on where I have some plasticity until I get up to this point. Which brings me back to this position 1. Or I can call that position 3. So 1 and 3 represent the same stress and strain. Now one thing I need to point out, again, this is idealized behavior. There are transient effects, and we'll talk about those things. But for now, let's try to keep things simple, where we take a look at these types of simple behaviors. All right. So this idea where this value is not as great as minus sigma yield, instead what is often observed is that this value, this range that we have here of elastic material behavior, elastic unloading, has a range of whatever this value is, 2 times sigma yield. So if this was yielding at 200 megapascals, we would have to unload 400 megapascals before we would get in to yielding and compression. Now that's 400 megapascals from whatever this highest stress was. So if we went up to 600 megapascals, we could even have yielding, in this particular example, before we're even in compression. We have yielding on the reverse side. This is an experimental observation, okay? And it's known as the Bauschinger effect. Let me write a few words down here while I pause the video. Alright, so a cyclically loaded material will yield during unloading or compressive reloading if the stress range is large enough. This is often modeled by an elastic zone of 2 times whatever the initial yield stress was. And again, we're going to talk about transient behaviors and stable cyclic behaviors and different things soon. Now, as I loaded back from 2 back up to point 1 or point 3, we have what's known as a hysteresis loop. And let's talk a little bit about the hysteresis loop that's formed here. Alright, so when we have that fully reversed cycle, this right part of this curve and the left part of this curve is known as a hysteresis loop. Okay, so some terminology that goes with it. So it is unloading elastically, for metals, a range of 2 times the initial yield stress. Once we get down to this maximum compressive stress, then it unloads elastically for a range of 2 sigma y, and it comes back here and completes this hysteresis loop. We would say that this distance from the tip on the left to the tip on the right is the stress range, the strain range, and the distance from the top to the bottom is the stress range. Again, I'm showing this for the case where we do have some plasticity. Now in my plot I showed stress as a function of time. It is possible to have strain control in a materials test where you would have strain as a function of time. So either one of these sets of axes can be controlled and the other would be the dependent variable. So the entire loop is called a hysteresis loop, but one side of the loop is called a hysteresis branch. See if I can just highlight this in a different color. So from here down to here, it's called a hysteresis branch. So just to highlight that, I'll put that in a different color. Now one thing that you may notice about the opposing hysteresis branch is if you have fully reversed cyclic loading, that other hysteresis branch can be modeled as if it's the same thing but turned and flipped. So from a mathematical functional point of view, if we have an equation that describes this branch on the right side, we have the same equation that we can use to describe the branch on the left side. They will be symmetric, or assumed to be symmetric. Now again, the interesting things that happen in materials are that not everything follows these rules. This is typical behavior. Now, another thing that is a little bit more subtle, but you may also notice this, is that this initial stress strain curve and the hysteresis branch have a very similar kind of behavior to it. They get to a certain value and then they start curving over. Here it doesn't yield until we get to the yield point, sigma y. But beyond that it starts to have some plastic strains, some changing of slope. Here we have an expanded range of 2 sigma yield before we yield in the cyclic case. And then we have kind of an expanded range of plastic behavior. This forms what we call the basis of Massing's hypothesis. The Germans probably call it Masing. It's going to be convenient for us, and basically it's a mathematical statement that the hysteresis branch is similar, functionally similar to the initial loading curve. Alright, so the hysteresis branch is functionally similar to the initial loading curve, but where delta sigma over 2, the stress amplitude replaces the stress in the function, and delta epsilon over 2, the strain range over 2, the strain amplitude replaces the strain in the equation. So, for example, if we have epsilon is some function of sigma, well that means that for our, this is for our initial curve, for our hysteresis branch, then what we can do is we can replace this as the strain amplitude is some function of the stress amplitude. Now we can do this for whatever functional description of the stress strain curve that we have, but for us it's most convenient if we use the Ramberg-Osgood equation. That's typically what's done, although like I said you can do this for other types of functional relationships between stress and strain. Alright, so we have epsilon is equal to sigma over E plus sigma over K to the 1 over N. We know this is our monotonic Ramberg-Osgood equation. And so what we're going to do is we're going to put in delta epsilon over 2 is equal to delta sigma over 2 divided by E. And so it looks pretty straightforward so far, but here's where the difference comes in. When we put in delta sigma over 2 in for sigma, that is inside of this parentheses. So that resulting quantity over our K, our strength coefficient, is taken to the 1 over N, where N is our strain hardening exponent. And so this has the ability to stretch that range out on the hardening part, the plasticity part of our hysteresis branch, as compared to our initial slope. Now this is for the strain amplitude. A lot of times we want to use this equation to calculate the strain range. So we would have delta epsilon is equal to, if I multiply both sides by 2, I would have delta sigma over E, then I would have 2 times delta sigma over 2 over K to the 1 over N. Now this delta sigma is from the origin of the tip that just ended. So what do I mean by that? If I have my stress strain plot and I use my monotonic Ramberg-Osgood equation, and I got to this position right here, so maybe that's my sigma 1 epsilon 1. I realize that's not an XY coordinate, but it seems more familiar to write it in terms of stress and strain. If I'm right here and I have a certain applied stress change or range, well, I apply that, plug that into this formula, I calculate the delta epsilon. So I'm down here somewhere, and the delta, the epsilon 2 point would be equal to the epsilon 1 point, in this case minus delta epsilon. And if I'm at this point and I apply the same stress change, I will get the exact same strain change, and I will be back at this point. Well, then my epsilon 3 would be equal to my epsilon 2 plus delta epsilon. So you see what's going on here. If I have a decreasing stress, I subtract. If I have an increasing stress, I add. So, we can say that the points, epsilon next, if you will, is equal to epsilon previous plus or minus delta epsilon, where the plus or minus is depending on if we have an increasing stress, and here the plus is for an increasing stress, and the negative if we have a decreasing stress. If I want to calculate intermediate points along the hysteresis branch, and I'm going to ask you to do that this semester, well, each intermediate point follows this equation, and follows this equation right here, but we just use a smaller stress range. So if I have a 500 megapascal total stress range, maybe I want to break this up into every 50 megapascal. So this would be 50 from here. This would be 100, 150, whatever it takes. So I plot all these points along this hysteresis branch curve. And then likewise on the upslope. Now, fully reversed cyclic loading is fairly convenient. It's very easy to do that. What gets to be a lot trickier is to plot these closing hysteresis loops if we have what's called variable amplitude loading. So let's talk about that for just a little bit. All right, to illustrate what goes on with variable amplitude loading, I think it's probably best if we start with a few examples. Now, for our purposes right now, I am always going to start at a very high level where I have exceeded the yield stress of the material, and I'll always end at that very high level. And we'll talk about why I want to do that later. But here's a very simple variable amplitude history. Here's one complete cycle right here, and there's another smaller cycle. So let's plot the hysteresis response for this. And I'll do my best. Sometimes this gets to be a little tricky, making these look decent. Let's suppose my initial stress strain curve was this dotted line, and so I use my monotonic Ramberg-Osgood equation for that. And I am now at this point right here, and I'm going to go all the way down, and I'm going to be yielding it in compression. All right, so I'm going to have my range, unloading with my slope of the modulus of elasticity. I have my range of 2 sigma yield, and then I yield. I'm down at the bottom point. I reload. I have a symmetric hysteresis loop. I'm back at this point, and now I have a small loop which I come down. Maybe I didn't even yield it. I'm going to show maybe just a tiny bit of yielding so we can see that loop, and then it closes back up. Now remember, our Ramberg-Osgood equation doesn't have a defined yield stress, so it is a continuous yield. So if you use this Ramberg-Osgood description, you will always have tiny widths to your hysteresis loops. They may not be meaningful, may be nearly all elastic, but in this case we have 2 closed hysteresis loops. All right, let's do another one. I'm up here. And I take these steps. So let's draw our hysteresis response. Monotonic. I'm going to dash that in. I unload a little bit. I reload. And I'll go all the way up to the top though, about here, and then I go back down. I close this hysteresis loop, and then I rejoin this curve. And I load it back up. Now I realize this is kind of hard to see. Let me see if I can zoom in on this part of that stress strain curve. So I'm here, and I get to this point. That's this location right there. I change directions a little bit. Okay, now I'm at this location. I have to go all the way down to this level before I close off this hysteresis loop and rejoin this branch. So now at this location, I've closed off that hysteresis loop, and then I rejoin this branch and continue on down to the bottom of the curve. And then I go back up and I close it out. So this is an important example to understand. This branch itself follows the massing hypothesis and our cyclic stress strain curve hysteresis branch equations, but it's only until I close it out. After I close it out, then I go back and I use this as my reference for my delta epsilons, and then I continue on as if this loop right here had never happened. I'm going to try to, maybe I can try to do something with Excel to kind of show this a little bit better. Let's do one more. Oh, maybe two more if I can make it look decent, but let's look at this one. Alright, so monotonic up to a certain level. I'm going to show a lot of plasticity, so I make this a little bit easier for me to deal with. I unload a little bit. At this point, I reload a little bit and then unload. From here to here, I have a closed hysteresis loop. Then I rejoin this branch. I continue on down to this point right here. I unload. I have a little bit of hysteresis loop from here to here, and then it continues. I have a closed hysteresis loop with this branch, and then I continue along the main branch again until I get down to this point. That's in compression, so I'll draw it down here a little bit. And then I have another one. Get to here, and then I get back down to there. And this entire curve is supposed to be a continuous curve down to this point. Then I reload, and I'm back up to here. So in this case, we have the one large loop, and then we have 1, 2, 3 small hysteresis loops. Okay, I'm going to try to do one more, and this one is going to be hard for me to draw and make it look anywhere near nice. But let's say we have our initial curve up to here, our initial loading, and we have a big decrease, but then we come up here and we have a smaller rise back. We don't get to this level, and these keep diminishing. But in the end, we finally get all the way back to where we started from. So this level and this level are the same. Let's see if we can sketch that hysteresis response. Like I said, this one's going to be a little bit tricky for me to sketch and make it look decent. Trying to give myself plenty of room. So we're here now at our first point up near the top, and we go all the way down to some big value right here. Okay, now from this point, let's label these A, B, C, D, E, F, G, H, and then this is I, which is the same as A. So here we have A, here we have B. Okay, so now from B to C, I'm up here. From C to D, and I'm drawing these with some width so we can see them. From C to D, we're here. From D to E, we're here. From E to F, we're there. F to G, we're here. Goes down a little bit. Maybe I went one too many points. There's H. And now we're sitting here at H, and I want to go all the way back up to level A. So when I do that, I first close off my loop from G, GHG. There's a loop that closes there. And then I close off my next loop. And then I close off my next loop. And then I close off the big loop. Okay, so these would be nested hysteresis loops. And this is an absolutely terrible looking sketch. But hopefully, if you try this on your own, you'll be able to get the idea of what's going on here. It has to remember every single point that we left off the stress strain curve until the loop is closed. Once each of these levels are exceeded, then we start to close off each of those loops. So I should have one big loop, and I should have 1, 2, 3 small loops. So I'm counting that right. So I should end up with 4 closed loops. So what I'm going to ask you to do then is to practice this for a few different stress strain curves, and we'll try to do a few more in class. Understanding this process is going to go a long way to understanding something called rainflow cycle counting, which is a technique for identifying closed hysteresis loops which are assumed to be damaging events in fatigue loading. So my hope is that we can talk and program in rainflow cycle counting as we understand how to construct these hysteresis branches in these different kind of examples. Alright, so again, the eventual goal is to write a computer program for a generic variable amplitude stress history. I will probably end up showing you how to do this in Fortran. Of course, you may want to do this in other languages, and that's fine. Alright, we have a little bit I want to talk about more in this section, and then we'll be done talking about uniaxial monotonic behavior in general terms. Like I said, I'd like for us to spend a little more time developing our program, but let's talk a little bit about transient material behavior and stable material behavior for cyclic loading. Alright, so let's talk about something called the cyclic stress strain curve and compare it to the monotonic stress strain curve. So let's draw our axes. We have sigma and epsilon. Maybe we're dealing with something like a low carbon steel. We know a low carbon steel will have a nice upper and lower yield point, whatever goes on around here. Do something like this, where we have this into the plastic range. If we were to unload this, we wouldn't see that kind of weird double yield point behavior. And then reloading it, we would get kind of a smooth curve like this. And if we were at a level of stress and strain that were not as high as this point that I drew here, we would have something like this, coming off of this curve, and then coming back here like that. Trying to draw these symmetric, I didn't quite achieve that, but we would have something like that behavior. And even if I was very near this value, maybe even up in this range of where this double yield point behavior is, if I were to keep cycling it, I would end up with something that would be pretty smooth. That double yield point behavior kind of washes out when we do our cyclic loading. So our monotonic stress strain curve can have kind of weird things going on, but our cyclic stress strain curve tends to look nice and smooth. So if I were to plot just the hysteresis loops, I'm exaggerating the amount of plasticity that we have here. The tips of the loops themselves kind of look like a stress strain curve. Again, it's trying to make it symmetric. But that dotted line that I drew in there, that's known as the cyclic stress strain curve. So the cyclic stress strain curve is constructed by connecting the tips of the hysteresis loops. And when we do cyclic loading, things we could have a stable material, we could have transient material response. we have to decide which hysteresis loop to use, because these can be a little different. Even though we're repeatedly cycling it at the same strain level or the same stress level each time, they can change a little bit. So often people use the half-life values. Okay, so in order to do this, then you're basically doing a fatigue test, and you're measuring these hysteresis loops. If it goes 5,000 cycles, then you take the hysteresis loop at 2,500 cycles. If it goes 1,000,000 cycles, well, then you take the hysteresis loop at 500,000 cycles, assuming you have any kind of width at all to it. Now, as compared to the monotonic stress strain curve, the cyclic stress strain curve may be different. So maybe that's our monotonic stress strain curve. And if I were to dash in the cyclic stress strain curve, the effective yield stress may actually be lower than the monotonic. But it still has a lot of features very similar to it, and so the same functional description that we use for the Ramberg-Osgood equation can be used for the cyclic stress strain curve. And so for us, we like to use, in this class, at least I like to use the Ramberg-Osgood equation. The monotonic curve would be sigma over E plus sigma over K to the 1 over N. The cyclic stress strain curve, we're going to use sigma over E. The modulus of elasticity really doesn't depend on the cyclic behavior. But we're going to change these numbers for the strength coefficient and use K prime and N prime. Alright, and so K prime is called the cyclic strength coefficient, N prime is a cyclic strain hardening exponent. In a very similar way that we can find K and N for monotonic stress strain curves, we can find K prime and N prime. We are using the tips of the loops in this case. If we plot log sigma and log, let's do delta sigma over 2. And log delta epsilon plastic over 2 for the hysteresis loop tips. So we don't have nearly as many points when we do this. We were to extrapolate this out to a plastic strain amplitude of 1, then that would correspond over here to K prime, and the slope of this would correspond to N prime. Now we kind of have a question. We've been talking a little bit about developing the Massing's hypothesis for the monotonic stress strain response. Well, we can use the cyclic stress strain curve and Massing's hypothesis in order to come up with our branch equations. So if we have cyclic data and the K prime and the N prime is different for cyclic loading than it is for our monotonic loading, then we can use our branch equation as delta epsilon over 2 is equal to delta sigma over 2 over E plus delta sigma over 2 over K prime, the 1 over N prime. So what I'm going to say is use K prime and N prime if they are available. Alright, so let's talk a little bit about transient behavior then. So we can cycle this in constant amplitude loading. And for purposes of our discussion right now, let's assume that we're in strain control. and we do a sine wave or sawtooth or whatever, that doesn't particularly matter for us at this point. But we will develop our hysteresis loops. We can increase the amplitude. We can get larger hysteresis loops as we have more plasticity and so forth. And we can construct our monotonic and cyclic stress strain curve. So let's see what a couple different behaviors might look like. Okay, we might load it up, unload it, reload it, and we can keep cycling it. And if we keep cycling it, and there really isn't any particular change to the points, the stress or the strain, depending on if we're in stress or strain control, then this would be stable, cyclically stable behavior. Now if we were to cycle it, again I'm in strain control, and under continued cycling, I end up having smaller and smaller strain levels. Well, let me do it smaller and smaller stress levels. I'm in strain control. Let me redo that plot. Okay, so in strain control, I'm getting to the same levels of strain, but I may end up dropping my stress level with continued cycling. This would be known as cyclic softening. And I'll draw it over here to the side. That the stresses start small, but they increase with each cycle. That would be called cyclic hardening. Again, in strain control. Now, there was a paper published in 1965 by Joe Dean Morrow called The Cyclic Plastic Strain Energy and the Fatigue of Metals. Joe Dean Morrow was at the University of Illinois at the time. And this is a very, very nice paper, very nice work. Joe Dean Morrow was a big proponent of the strain life fatigue method. And if we look at one of his figures here, this kind of shows the picture of what goes on in this cyclic hardening, softening, or cyclically stable material behavior. Now this is copper. There's 3 heat treatments of copper that have been done: fully annealed, partially annealed, and severely cold worked copper. And these are actual experimental data traces. So back then they didn't really use computers to digitize data. They'd have a chart recorder that would do an XY plot. So, and not every cycle was recorded, but a lot of them were. So this is the first cycle. Okay, and then you can see, you can follow the trace. This is in strain control. This is the 3rd cycle. And so this fully annealed copper tends to cyclically harden. So you see the stresses going up this axis. Here's one that's partially annealed. So you get the first cycle, and then some cycles it kind of hardens, some cycles it softens a little bit. It's sort of a cyclically stable type material on the average, I guess you could say. But here's one that's been severely work hardened, and it starts very stiff, but as the cycles increase, the stresses decrease. So one of the big things to get out of this paper was that he was able to show that cyclically very soft materials tend to cyclically harden, very hard materials tend to cyclically soften. So cyclic loading tends to take away some of those effects that you may have wanted in your material. Maybe you wanted your material to be fully annealed. Well, when you do cyclic loading, you're working it. You're building up dislocations again after they've been annealed out, and that's going to change the material response. If you have severely worked your material and you start doing cyclic loading, well, maybe at that point you're starting to break free some of those dislocations around whatever obstacles have developed, and you're going to end up cyclically softening. So cyclic loading tends to take away some of these extreme effects that you might otherwise see. Now, in general terms then, if we wanted to plot our monotonic and our cyclic stress strain curves, if we have a material, one example was 2024. It's kind of a soft material. If we did half-life hysteresis loops, then our cyclic stress strain curve might end up here somewhere. And I realize there's various heat treatments and things like that, but this is just an example of what can happen. Here's maybe a stainless steel. It's a very strong material, has a kind of a high slope to it in the plastic range. But if we cycle it, we may end up with a softer material behavior. And in general terms, we can express this in terms of the strain hardening exponent, the monotonic strain hardening exponent. Now I'm going to put this down here, and I'm going to try to emphasize that this may or may not happen, but if you have no other indications for cyclic hardening or softening, then if you have a strain hardening exponent that's greater than 0.2, it will tend to cyclically harden. And if you have a strain hardening exponent that's less than about 0.1, it will tend to cyclically soften. Now, I'm not saying that this has to be. Don't take these numbers as absolute truths. If you have experimental data and your monotonic curve has a strain hardening exponent of 0.25 and you observe through cyclic tests that it cyclically softens, well, trust your experimental data. So these are just very generic kind of rules of thumb. So what are we trying to get out of all this in this lecture? We talked about cyclic behavior. We talked about the cyclic stress strain curve and how to get that from the hysteresis loops. We've talked about the Massing's hypothesis and the Bauschinger effect to have a mathematical model for our hysteresis loop branches. All right, I think that's good for now, and we're going to start to get into, in our next lectures, some more general continuum mechanics, because in the end we want to do all of this that we talked about for uniaxial behavior. We want to come up with all these types of models and simulations for multi-axial behavior. We have a lot more freedom in multi-axial loading. For example, we have shearing stress and normal stresses that we can apply, and we can have various loading paths. And one of the interesting things about plasticity is that because it's a non-conservative type system, you're expending plastic energy. You're expending energy from the loading cycle to deform the material, to heat it up, to do these different things. You're going to have some path-dependent effects. So applying tension and torsion, or applying torsion and tension, may give you a different plastic stress strain response. So we're going to investigate these things. So first, a little general continuum mechanics. We're talking about strain in the general sense and stress in the general sense. And then we're going to get into invariance of the stress tensor, which will lead us into J2 flow theory.